Flying high with math. Discover exciting math applications in aerospace. Mathematics is used across aerospace, from designing and manufacturing aircraft, to support and services after delivery, and to sustainability across the life cycle. We are now going to describe some exciting ways we have used math to solve aerospace challenges. We will first give an overview of how we've used math to determine the best way to order wind tunnel tests. We will then give an overview of what we specifically do as mathematicians. And finally, we'll review a variety of different examples of how we use math in the aerospace industry.
Model aircraft are used in the aerospace industry to test different designs in wind tunnels. This helps determine what new aircraft should be built. Thousands of different designs are tested. The best order of the test needs to be determined so that the test can be done in the shortest amount of time. In general, the best order comes from grouping together tests that are similar and so don't take as much time to change between as other groups of tests. You can imagine that the challenge of determining the best order of tasks is a common need. This need is a variation of a well-known challenge called the traveling salesman problem. In the traveling salesman problem, the salesman has to visit a number of cities and return home. The salesman wants to be home as soon as possible. Ordering the wind tunnel test is a similar math challenge. We want to complete all the tests in the shortest amount of time. Opportunities like these come up frequently across the aerospace industry. For example, we determine the best order for a robot to drill holes when building part of an aircraft. Because these opportunities come up frequently in the aerospace industry, we have a math algorithm and computer code that can determine the best order of tasks if we are given the time it takes to change from one task to another. We have used this same code for all of these challenges and others. This reuse of the same code to solve what seem to be very different challenges is one aspect of what being a mathematician is about. And we are now going to give more insights into what we do as mathematicians. As mathematicians in industry, we typically go through the following 6 general steps when we solve math challenges. The first step is to partner with what we call a customer to understand the challenge that needs to be solved. For example, in the case of the wind tunnel challenge, this step was easy. We had been working with this customer for a number of years, and he was familiar with a lot of the math we had been using. He realized that determining the best order of wind tunnel tests was similar to a traveling salesman problem, and so he thought to ask us if we had an algorithm and computer code to address his business need. And sure enough, we did. We gave him the computer code, and he was able to use it to develop a tool to determine the best order for wind tunnel tests. In this case, it did not take long to understand the math challenge that needed to be solved. In other cases, especially if we have not worked on similar opportunities, it can take longer. But overall, the first step is to partner with our customers to understand the business opportunity that needs to be addressed using mathematics. Once we understand the challenge, we write mathematical equations describing it. You will see some examples of equations in later slides. This step helps us make sure we understand the math challenge and helps guide us in the algorithm development and implementation. When we have the mathematical equations, we determine the algorithm we should develop and then write computer code to run the algorithm. An algorithm is just a sequence of steps taken with data in order to determine a solution, for instance, the best wind tunnel test order. After we have completed the computer code and done a lot of testing with different data, we present the results to the customer. We work with the customer to make sure the results are what is expected. Sometimes we might make enhancements to the challenge to be solved and then update the algorithm and computer code. Finally, we transition the code to the customer so that he or she can use the code to address his or her opportunities. For example, the wind tunnel test ordering opportunities. This was a high-level overview of the general steps we take to solve math opportunities in industry. The amount of time spent on each step varies from challenge to challenge. We will now go through a variety of different examples of opportunities we use math to solve, using the steps we just discussed.
In the aerospace industry, and really in many industries, statistical methods are commonly applied to understand and ensure product quality. We work closely with our suppliers, and they produce parts for us to use and deliver parts to us once the parts pass their initial quality inspections. Then we receive the parts and use statistics to check for quality as well, such as checking that they are the appropriate size, shape, etc. We can apply statistical process control methods to look at a sample of parts and use math and statistics to understand what that sample tells us about the whole population of parts. This enables us to sample hundreds instead of thousands of parts when we receive them and look at things like average lengths or size or weight, along with the little differences from the average of each part. What's more, we and our suppliers can use the same mathematical concepts to keep track of part quality over time. Statistical process control helps us determine if we can accept parts delivered from our suppliers. This is a great example of using statistics to help inform decisions in the aerospace industry.
The Boeing Confident Travel Initiative was developed to evaluate and improve the safety of the air travel system during the COVID-19 pandemic. Mathematical models using computational fluid dynamics were developed to track the movement of particles from a COP throughout the airplane and compare it to other indoor environments, such as an office conference room. The results revealed that sitting next to someone on an airplane is the same as sitting 7 or more feet apart in an office conference room. These results were validated through testing on actual airplanes conducted by the U.S. Air Force. Additional models include a mathematical model for the entire air travel journey, including walking through airports and riding on shuttle buses, and a statistical model to evaluate the performance of COVID-19 testing strategies for international travel.
Another area where math is playing a big role in the aerospace industry is in the design of our airplanes or vehicles, especially when it comes to the shape or the geometry of an airplane. We are building geometry models based on parameters that describe the shape, and then we use optimization methods to find the optimal shape or geometry. For example, we might want to try to find a geometry that minimizes the fuel consumption while at the same time making sure that the airplane we're designing can reach the airports that we want to reach. So to do this, we built some specialized geometry tools that sometimes even incorporate math formulation to ensure a specific geometry always satisfies some underlying math and physical constraints. And the example we show here is of a hypersonic vehicle where we use the Taylor-Markov equation and enforce that the geometry that we use always satisfies that. We then take these tools and combine them with simulations that predict how, for example, the air flows over that geometry, which then allows us to, for example, calculate the fuel consumption or other behavior of the airplane. We then take that and find the right parameters using optimization methods that give us the best performance. To do this, we run lots of simulations that are very compute intensive, which is the reason that we have some of the largest computers in industry to help us do that cost effectively and fast. Doing this leads to a good new product that the company can sell and create lots of business.
Another interesting application of math in aerospace arises in the context of painting exteriors of aircraft according to customers' desires. See the upper right picture of a R2-D2 rendition and a matching color aircraft. Traditionally, matching colors using paint is a visual guess and check method, but here we describe a mathematically based approach using geometrical methods to more precisely and efficiently produce the desired result. The problem statement in either the traditional or mathematical approach is the same. How close of a color match is possible? In the mathematical domain, we begin with a computerized definition of what colors can be exactly matched. These colors are defined by what is called a color gamut. See the right-hand side of the slide for an example of that. A color can be precisely matched if it is inside a specified color gamut. But what does it mean to be inside a color gamut? After all, as we see from the slide, it is a collection of color points. The lower portion of the slide illustrates one solution: enclose the gamut into a closed surface. Now we have one answer. If a color is inside that closed surface, then it is exactly reproducible. This, by the way, is how color printers operate. Now suppose a color is outside that enclosed color gamut. The question then becomes, how close can one get, right? That is, what is the best obtainable color match? The extra challenge here is that measuring spatial distance between 2 points is not the same thing as measuring human perception between 2 colors. In fact, there are various and evolving ways to measure human perception differentiating colors. This is an area of research referred to as color science. Partnering with chemical technology engineers, we constructed an effective solution that has been recently patented.
To predict how well a given design will perform in real life, complex mathematical equations must be solved, describing the airflow over every surface. These mathematical models, like models of many physical phenomena, are typically described using partial differential equations, like the Navier-Stokes equations seen here. This discipline is also called CFD for computational fluid dynamics. To compute these solutions, more often than not, the approach is taken to divide the problem into many much smaller problems and compute these more manageable problems independently. For example, to simulate the flow of air over a wing, you can divide space up into many small neighboring volumes and find how the flow behaves in just each little region. Then all those smaller solutions can be assembled into one result that describes the flow over the entire wing. This approach requires either a lot of time or a lot of computing power, because you need to perform the same calculation millions or billions of times. Because solving such complex equations is an important area when designing aircraft, we have high-performance computing clusters available dedicated to tackling complex mathematical challenges just like these.
As we saw through those examples, mathematics is leveraged to solve a wide range of aerospace challenges, from how we design and build aircraft to providing support after we deliver to customers. We hope you enjoyed these examples of how mathematics is used in aerospace and are excited about pursuing careers using mathematics in industry. Lastly, we'd like to thank the Boeing applied mathematicians who contributed ideas and examples for this presentation. Thank you.